So I'm not sure the video is gonna play right for you guys, so I would just like to maybe skip over it, because I think so. The main message this video is trying to convey um, is that over the past 5 years or so, we've improved our development processes quite tremendously, right? We've um, managed to revolutionize the space of how we build, how we test, and and how we continuously optimize our code, right? So the basic idea of what all of the CI tools and services allows us to do is really to strip away all of the overhead that goes around shipping code, and really allows us to focus on the core ideas. So in the analogy of a space ship or a rocket ship, um, the way that you will probably relate to it, the way that we currently build code is around, like, we have to build a core idea, and then we have a variety of tools and services that we use to for containers, for source control, for deployments and monitoring, unit testing. We have automatic, from the minute we commit change, we have tens or hundreds of continuous integration tasks that are kicking off and making sure that everything builds correctly and is deployed automatically. And we've gotten to the place where we really don't have to spend a lot of time on all of the menial tasks of making sure that everything works every single time we want to push new code out. And specifically, I think with client-side frameworks like Angular and React, and server-side frameworks like Ruby on Rails or Django or Node.js or whatever, we've gotten to the point where all of these menial tasks are automated through simple APIs, and then we can just focus on our core. But the one place I think that this revolution is still decades behind is in the domain of data warehouses. I'm trying to get slide to update. Okay, here we go. So yeah, when you think about it, if you compare how you build code and how you push changes to your databases or changes to your infrastructure or changes to your architecture, and you compare that to how you update your data warehouse schemas and configurations, you would clearly see that we have to spend so much time on making sure that every change we do in production, we have to go back to the data warehouse and apply the same changes. Usually we do it through scripts that we've written over the years, or just manually logging in and changing data types, or changing or adding columns or removing columns, stuff like that. So there's always this delay from the minute that the code changes, like we introduce a new module or a new piece of data, until we get to the point where we have the data available in the data warehouse in a way that's usable, right? It's not just about adding the new data, it's also about choosing the right indexes, the right distribution to make sure that it's actually usable. And what I've been seeing over the past 6-7 years in data warehouses, that usually this is a process that takes months after the main model comes in, and takes a lot of manual maintenance to check everything and see that it works. And then a couple of weeks later, you might run into more issues with specific queries that needs additional optimizations. So really, I think the idea that we were looking for at Panoply is how can we improve get faster iterations and little maintenance, and remove all of the manual menial tasks that need to be done in order to make sure that data warehouse is in sync with the most up-to-date version in production, with all of the data and all of the correct data types and the right configurations, like performance configurations. So I think the point that we were trying to think about is how can we take all of these tasks that are usually done manually and create a process that can continuously optimize and get all of the data um, in sync in minutes. So we commit a new piece of code and automatically we'll have a data warehouse update to reflect these changes. So if, for example, through a configuration file or through any other kind of API, we want to add data, change data types, change the way we query the data or stuff like that, we wouldn't have to manually do anything. We just commit the code and we know that minutes later we'll have the data warehouse completely in sync. So to do that, I went back to this quote that I really love, and I think it applies to pretty much everything in programming and software design. That what we wanted to do is have to make changes easy, and that might be really difficult, right? We need this framework or a process that we can just push a configuration file in and know that we'll have this CI process take it off and readjust and make all of the changes that are needed and run the tests and make sure the whole thing is usable. And then once we have that, making changes is as simple as just pushing commits, really simple. So in terms of what kind of changes we see in data warehouse integrations, or what kind of changes we would like this process to be able to support, the simple one is just data changes, right? This is simple because it's really well defined. You know exactly what kind of columns, tables, data types we want, what kind of constraints we have, maybe compression that we want to use, and it's pretty easy to reason about. And you'll see in a minute how we do it. But the more complicated one is queries. That's far more complicated because we can't really reason about it, as you'll see later on. We can probably, if you put your mind to it and spend a couple of hours or days, you can probably map out what are the business questions, what are the decision-making processes that need to be made, and based on that, infer what would be the most common query types, what kind of indexes we should use, what kind of distribution we should use. But then everything might change a day later. And of course, as the problem grows, and as you have hundreds or thousands of tables, columns, it's really easily becomes something that's just impossible to chase. And what you'll probably relate to it, that the process of applying changes to the schema that are around performance optimizations for queries is something that's usually really reactive, right? You have an analyst, or you have an analyst coming to like tell you there's this query that doesn't run well or doesn't run at all or crashes or whatever, or you try to run something and you see that it crashes, and then you try to react to that and you try to make a change and you hope that that change wouldn't hurt something else. So this is a more complicated change to reason about, the change of query behavior, like how people are querying the data. So we'll start with the data and metadata changes and the process we've created Panoply. What you see here is the evolution of messaging app, where over time we had more commits, adding more and more functionality, more and more logic. You know, we started just with having simple users, then we had messages, we added user sessions, like session time, made some changes to the names, for example, session time ranges, and finally we wanted to add the ability to send messages to groups. Now this is really simplified, but the basic idea still holds, and I think like this is based on a real life example, obviously really simplified to just make the point, but we did work with a company doing something really similar, and over time we've seen how it evolved and how a model that started really simple just by adding users and messages to simple data models that were reflected in the data warehouse over time, they made changes, they changed data types, they changed the complexity of the data, the relationships, and obviously um, the type of queries they can learn from it. So going back, oh, so yeah, what we wanted to do in this example is think about how do we make sure that every commit that adds a new layer of logic, adds a new model layer or a new type of data will be automatically reflected correctly to the data warehouse. There are a couple of ways to do that, but the approach that we went with is declarative. So what we wanted to do is have this simple schema YAML file that we just keep updating, and we basically, it's kind of like a database migration configuration file, where basically with every commit, we can also update this file and say, okay, for table users, these are the columns we want to have, these are the types of the columns. We can change data types, we can add new columns, remove columns, and we do that without even ever connecting to the database. What we do is we just update this file, we commit it, and then we have a continuous integration process that picks up these changes and apply them to the data warehouse. So it is able to basically compare whatever this file has to the schema in the database and say, hey, there's a new column here, I need to edit. This is the column that must have been removed, I need to remove it. There's a data type change. There's a new foreign key here through the references point, etc. So, it just applies whatever we have here. And obviously, if it fails, it can roll back and just reject the whole build. And finally, what we were thinking of, and we can probably take it one step further and say, you know what, we can generate this file from, if you use a ORM kind of thing, like Django or Ruby on Rails, that generates a data model. We can actually use that generated data model to generate this file. So even this step might be redundant, and we can probably remove it in some apps. But in other cases, it's really common to realize that there's sometimes not a one-to-one correlation between the data warehouse and the actual production database. You don't want it to be exactly the same. Maybe you want to add transformations, or maybe you want to not copy all of the data or anything else. So for that reason, having it as a separate file really helps. But the idea still holds. Nobody needs to connect to all of the databases we have. Nobody needs to apply these changes manually after the commit. It just happens all at once. So this is the process of what I was just describing. We make changes to this YAML file. This YAML file, we have a remodel CI task that looks at this YAML file and compares the data it has, the columns and the tables and data types and the references and everything, to what we have in the database, and then it applies the required alter table commands or create table commands to make sure that the data warehouse reflects exactly what we have in the YAML file. And of course, like I was saying, when it fails, it can just reject the whole build and roll everything back. So you can think of it just like having your test fail, right? If for some reason someone is trying to make a change that doesn't make sense, or that there's a problem, it will roll back and be rejected. But once the build is completed, you are confident that the data warehouse reflects exactly what you have in that file, and that saves a whole lot of headache. I don't think I have enough time to dive into this slide, but just generally, there is a problem when you're thinking of a case where you have many concurrent commits happening at the same time. You will have some problems with concurrency where several changes are trying to happen at the same time, or that there are maybe conflicts in the generated schema files. And that's really easy for us to solve, and that's one of the cool benefits here. If there are conflicts, if you have two developers trying to make changes, they will have a conflict on the source control even. They will get it way before you would usually get it when data engineer or someone will need to log into the database and apply all of these changes, because they will see it when they try to commit, when they try to push their code, if there's a conflict, they will need to resolve it right then and there. And you wouldn't have to have someone try to figure out what the right conflict resolution should be a couple of days or weeks later. But of course, so the process that we have here is that if there is a new commit coming in the middle of a remodel process, we just roll it back and start all over with the new commit. In Redshift, I think this is pretty well known, but just I want to touch on it. There's a problem with changing column types. You can't really do it in Redshift. Obviously, the common solution is to add a new temporary column, copy the data. You can see the process here. If we tried, for example, to change the date field here from date to a timestamp, the created field from date to a timestamp. Usually what you do, you create a new column. We call it here created temp. We copy all of the data over with this update SQL command, rename the column, and then drop the old column. This is, I think, pretty straightforward, and we do it obviously, like I was saying, automatically. That's the whole point of this talk. That you don't, I think every time you have to log in and like try to apply some SQL code manually, I think you're definitely doing something wrong, because over time it won't be sustainable, and it's really error prone. But the problem with this approach of creating the extra column and dropping the old one is the problem of view constraints or dependencies. Basically, what happens is everyone that has done it has probably run into this problem where you try to drop a column and you will get this error telling you that there are dependencies on that column. So for example, if you have a view that queries the column and you just change the data type and you did the rename, and now you're trying to drop the column, the old one, Redshift will complain, tell you, look, you can't remove this column because some other view assumes the column is there, and if you remove it, something on that view might break. And that's a really annoying problem to handle all of the dependencies. The same happens, by the way, for foreign keys. So if that column is also a foreign key on a different table, it will similarly complain. It wouldn't let you just drop it. The way to fix it is to, and that's kind of, I think this is an example of where you want to code it and you don't want to do it by hand, is that you need to basically drop all of the dependent objects, like the views, the foreign keys, whatever it is, apply your change, so make the column name change or the column data type change, and then rebuild everything, all of the views and all of the foreign keys. There is a helper table in Redshift and Postgres called pgdepend. You can use it. It really shows you all of the dependencies that you have. So for every column, it shows you which other columns and objects are dependent on it through foreign key or view or anything else. And you can use that. That's what we are doing at Panoply. So the remodel step that we have, what it does is it queries this table, finds all of the dependencies, uses it to generate basically a graph that we can traverse to find all the way over all the way through all of the ancestors, find all of the dependencies that we have, and then we know specifically which views and foreign keys and changes we need to apply. We remove these specific objects, and then we rebuild them obviously in a transaction, so we'll be able to roll it back. But I think this is, while it's a little bit cumbersome, it's really simple to reason about. Query changes, I think, is the other type of change. So this wouldn't be able to be reflected in the schema YAML file, right? Because the schema, the data types are pretty much the same. You might think of it as, as you get people or queries that are different, and people are querying different columns and are filtering by different columns or aggregating or whatever joins by different columns, you may want to use that information to basically generate a new schema YAML file that also adds parameters like should it be a sort key or should it be a distribution key, and then apply these changes. We don't do it this way, so we don't really go back to change the schema file itself. Instead, we have these two parallel processes. One is for applying all of the metadata changes around the column types, column names, stuff like that. And then we have this other process that focuses on reacting to new types of queries and changing basically the sort keys and the distribution keys to ensure that we get the best performance. I'm sorry, guys, I will need to be a little bit quicker here, so I will need to skip over some of these slides. I will just give you a sneak peek and maybe give you some idea of what you can look into. So first of all, the idea of ETL versus ELT, I think now you know that ETL basically stands for extract, transfer, and load. It's a process where we read data from one source. It can be your database, it can be some web API like Facebook Ads API, Salesforce API, whatever. It can be files on S3 or anything else. And then you apply some transformations to it. Usually this is hard-coded scripts that read the data and changes it in some way, and then you load the data, the modified data into Redshift. We are taking a different approach. The concept called ELT, which is extract, load, and transfer. And basically the idea is that you want to first extract the data from the source, immediately load it as is to the data lake or data warehouse. In our case, it's Redshift, and then transform it while it's already in Redshift. I'm sorry I don't have much time to elaborate on it, but if you do make this change in architecture and really think about it differently, and you think about how you first load all of the data, and you basically get to the point where you have all of your data in your data warehouse as raw data, but then you have transformation views that are basically applies all of your transformations SQL code. You end up with both having the raw data always immediately available, really, really fast as soon as the data is in. You don't have to wait for long transformations to run, but you're also able to query aggregations and enhanced data sets that are really useful for analytics. Of course, one of the things we do here is that after we load all of the transformations as views, we apply selective materialization, which basically means that if there are some views that are really under a lot of use, we might choose to materialize them into a real table. So again, you will get the real-time performance you would get out of having the data pre-transformed, but you will also have the flexibility of applying changes and iterating on it, and over a couple of minutes later be able to see the changes again without having to take your transformation code, change it, and have to wait for several, maybe hours for the whole thing to run just to see the result that you're getting. Sort keys. So sort keys and disk keys are the main topic here in this talk. And because I think these are the ones that are most complicated to reason about and takes a whole lot of time from data engineers. So really the question is, how do we pick the right sort keys and distribution keys, and how do we do it continuously? Again, I don't want to have someone have to spend time looking at queries or trying to come up with some kind of an idea of what people might be using. So a quick recap on sort keys. Sort keys are the way that Redshift basically stores data sorted in files. So basically Redshift stores all of the data per column in 1 MB blocks. These are the underlying files that it uses. And if you're not using any sort keys, it means that each file, each one of these blocks, will contain a mixture of all sorts of values. There's no way to know what are the values without actually opening the file and reading it. And that means that if you're not using sort keys, you're basically, every query that you do has to query that obviously doesn't use sort keys, has to read all of the files from disk, read all of the content of the entire database, or at least specifically on that specific column, and has to read all of the data from that column, read through it, and then decide, if this is something we can use. So it's kind of like, I think it's a little bit comparable to indexes. If we do use sort keys, we can define that we sort the data in some way, and what it will mean is that two things. It will mean that within each block, the data will be sorted in a certain way, so you know that as you read through it, the values will get bigger. But it also means that we can easily reason about and measure the minimum and maximum values of each block. And that means that we can skip blocks. So when we read, when we filter a table by, we do a where by some value, in this case it's like gender equals male or female, the database, Redshift, doesn't have to open and read all of these files and just skip some of them. So obviously that makes sense for scanning. So let's look at an example and see how we can optimize it automatically. So this is a really simple query that basically you can see based on this explain output that most of the time, obviously, in this query is spent just doing the scan, just reading from files. This makes sense because the operation of just count is really negligible compared to having to open potentially, terabytes of data or files and reading through them, all of the bytes, and then parsing them and fetching the results. And one quick note about explain in Redshift. So this table called STL explain, I think it's wonderful. I really suggest you look at it because it gives you actual explain output of every query being executed in the database. So that allows you to retroactively look at a query and see exactly what it did, or at least how the planner planned it. The cost, as you can see here, I'm sorry. If you guys aren't familiar with the concept of query cost, I think it's a whole subject, but just generally, you can think of it as, it's just a number. It doesn't indicate any, it doesn't specify any specific unit. It's not like in seconds or megabytes or anything like that. It's just a number that the query planner, Redshift query planner, uses to estimate the time cost of several different query plans. So if the query planner might have several different ways to execute the same query, and it would use this number to assume or estimate which of the different query plans will be more expensive than others. So while this is a really risky number and paying too much attention to it might lead you down a rabbit hole that will give you even worse results, but you can use it to reason about what is within the query, what is probably the most time-consuming task. So here, we read it bottom up. So we see that the scan takes whatever, some X amount of cost, and then the aggregation is pretty much accumulative. So that means that the numbers at the top will include the numbers at the bottom. So you can see that the aggregate phase here really doesn't add a lot compared to the step of just scanning. And we can see the filter information in STL explain. Now, Redshift has another table. It's called STL scan. This table shows us for every scan that reached the database, we can see first of all, how much time it took to scan that specific file or slice, how many rows were produced, and how many rows existed before filtering. So that really shows us easily. We can see that about half of the data we had to scan in this case is basically goes to waste. We are not using it because it's being filtered out. And that clearly is a great opportunity for optimization. But if we can decide to just not read this other half, we'll save about half the time here in this specific query. So by looking at STL explain and STL scan, you can figure out which columns will contribute the most to reducing the time you spend in scanning. So what we have, you will see it in a couple of slides later on. But basically what we do is we have this process that we read STL explain and STL scan periodically, about every couple of days. We fetch all of this data, and we create a mapping for each table, looking at all of the queries that were executed. We get for each table and each column how many times it was scanned, what was the cost of this scan, and basically how much overhead we had for this scan. So in this case, it's about 50% overhead. So 50%, I don't know if overhead is a word, but wasted time in this case, inefficient scanning. So we can, once we have all of these numbers for all of these numbers for all of the columns, we can easily sort them out and really see what are the top ones, what are the ones that could take the most amount of time or indirectly cost, and have the greatest potential for improvement. Because, like, if you take an extreme example where we filter a column and so post filtering, we just have 10% of the data compared to like whatever we had before the filtering, we can clearly see that we're doing so much wasteful scanning. It makes no sense. But if it's the other way around, like if we have a filter that has to scan all of the data, but 90% of it does end up being used, then we wouldn't get a lot out of optimizing it. So really, the process of trying to figure out where we'll get the best benefits is what our process does. And at the end, in a little bit of time, like in a couple of slides, I will show you exactly how it all comes together to create a single process that kind of reasons about all of these decisions. Let's talk about distributions. So distribution keys are the way that basically Redshift distributes data across the nodes in the cluster. One thing that's important to note is that Redshift is columnar, so basically it means that it stores every column separately in a single file. But in terms of its distribution, it's row-based. What it means is that the same row with all of its columns will always end up in the same node. You wouldn't have a row like broken into several nodes. And that means that the distribution, the way that you make the distribution choices apply to the whole row. And basically what it is, it lets Redshift know for every given row, where should Redshift put it? And obviously it plays a huge role in collocation later when we need to join stuff up, as we'll see in a minute. So let's just do a quick recap. Even distribution is default. Even means that you just push rows in and they will be evenly distributed across all of the nodes. And generally, it's the default, and it's generally great because it guarantees, again, that it's even. And that means you don't have bottlenecks. You don't have one node spiking at 90% disk space and maybe 9% CPU, and other nodes are sitting almost idle. If you use that, you can be pretty sure that you'll get all of the nodes to participate to the best of their ability. But it does mean that sometimes when you need to join stuff up, you'd have the rows distributed on different nodes, and you will have to spend a lot of query time just to reshuffle the data between the node to be able to complete the join. Key distribution is also pretty straightforward. It basically tells Redshift, look at one key, one column in the row, and make sure that all of the values that have the same, all of the rows that have the same value on that column will end up in the same node. So if we do it by gender, for example, it will make sure that all of the females will be in one node and all of the males will be in another row, in another node. And of course, like I was saying, it might end up with uneven distribution, but if we're joining based on gender very, very frequently, we'll get to the point where we don't need to do a lot of shuffling because every node will be able to complete the join by itself without having to communicate with any other nodes. So we'll get really high speed, massively parallel query execution. And finally, the last one I think that is really less used, but I think it's just enormously useful in some cases, is all. All tell Redshift to just duplicate every row to all of the nodes. And it might seem wasteful because you really, you create a lot of duplicates. You have to pay when you write them, and you have to pay in storage. But for some cases, as you'll see in an example in a minute, you end up in small tables that aren't frequently changing. You end up with getting just the best of both worlds. You get both great even distribution, and you get collocation because every node is able to basically resolve the join separately and independently. So I think let's look at. So this slide shows a little bit, I think, of how the how the distributed joins work. So really the idea is in this example that we are just trying to join users together based on their group ID, right? And basically when you think about how joins work, they always have a concept known as an inner table and an outer table. And and it's not related to like inner join or outer join. In the inner table, you will see it in the explain output, is usually the smaller of the two tables in the join. So here, for example, we are joining the groups table with the users table. The groups, there are much fewer groups than users in that specific example. So the query planner will probably choose the groups table to be the inner table. And then what it does for distributed join, it will send the inner table around between the nodes such that either they all have the same, like a duplicate of the inner table on all of the nodes, or it will have just a partition of it. But in both cases, there's a lot of shuffling that has to take place, right? It needs to read this inner table and shuffle it around, transmit sometimes the entire table over the network. So let's look at a pseudo real-life example that we had, looking back at the same query that we had. This is the explain output of that query. And again, going bottom up, you can see that scans here are really negligible. We have two scans, one scan on table groups and the other on table users. Then we have a join that you can see by the cost. It just takes thousands times more execution time to basically to complete the join. And finally, like the upper stages, the hash aggregate and subquery scan and hash aggregate again are just negligible, are nothing. So really you can clearly see where the bottleneck in this query is. And the key thing to note here is that this step that says hash full join, it gives us a little hint about how it did distribution. So how it moved the tables around to make sure that every node can complete its join. And in this case, it told us that this is dist both, which we'll see in a minute what it means. So basically, the way to look and understand what the database is doing is by um, this format that tells us how the distribution works. So DS is just distribution prefix, and then we have two types of algorithms to basically send the data around. One is dist, and the other is broadcast. So this is what it's really easy to think about. This is just means that um, it redistributes part of the data around. So for example, if we have a big table that has hundreds of values, it will basically segment the values into ranges. It will say, okay, range 0 to 100, 101 to 200, etc. And will allocate different ranges to the different nodes. It would basically assign a node to a sub-range of the data. And then the table gets reshuffled around, but only a segment of it ends up on every specific node. Broadcast is much more expensive in terms of network. If you see broadcast, it's sometimes really worrisome, depends on how big the data is. Broadcast means they basically duplicate the entire table over and over again to all of the nodes. And you will see it really often in Redshift. There are some queries that must use broadcast, like theta joins or like really complicated joins. And in these cases, you basically duplicate the whole table around all over the place. And that's where you really want to think about maybe you should do distribution all. Because when you think about it, when you run the query, the database has to basically broadcast or duplicate the entire table, which will end up in this exact same result as you would have had if you initially used distribution all and just duplicated the table once instead of on every query. So sometimes I think if you see broadcast coming up a lot and you don't find a better way to optimize it, it might be a good indication that maybe you should use distribution all here. And finally, the last part of the format, it's either both outer, inner, or none. It basically tells you which of the two tables had to go through the distribution step. So regardless of if it's a broadcast or a distribution, it might be the inner table, which is probably best. Well, none is the best because nothing needs to be reshuffled. But the next best one you will see there is inner, because it means that the smaller of the two tables is being distributed. Outer is usually much more expensive because it's a bigger table, and both is horrible. It means both of the tables has to be reshuffled. And that's what we had in the previous query, and probably this is what you're going to see in most of the queries you run, because that's pretty much the default. So I don't have enough time to go into this slide, but you can keep it for reference. Just a little bit of visual explanation of what the different values might be and how the data is shuffled around. But you can see that distribution both at the bottom there is one of the more expensive situations you can have. And this is usually the default in Redshift. So if you don't optimize anything, you don't change anything, this is usually what you get. And with simple changes, we can get much better. So in this case, in this query, what we've done is we've set the distribution key on both tables, the groups and users, to be the group ID, and you can see how much better this query is now looking. There's a much lower overhead, there's a much lower execution time, and distribution is now none after making this change. There's a bigger example here. You shouldn't read the code, but it's a real-life example generated by Tableau. And that's usually the type of queries we are seeing. The one that I showed before is more of a, simple one just to make the point, but this is a real-life example we're actually usually seeing. And right, so I don't have enough time to go into all of the specifics of how the different steps are built in that query, but you can see just generally. You can see here all of the maybe I have it. Oh, okay. So this is the result of the explains. After I cleaned it up a little bit and just left the join steps, there are 4 levels of joins here. And you can see the cost, how it goes up. And really the process that we're doing, and we were able to analyze this process and build a script that automates it, is basically we find the most expensive join point in terms of cost, and we look at the information we have about how the join was made, what kind of fields were used for the join, and then we either use a distribution key on both fields. So for example, in this case, the top one, which I think were the most expensive, we used user ID on both the session table and the users table. And then the next one also, we user ID on the users table and the messages table. So this is really how the process works. We find the most expensive one and we try to optimize it and find the best results. And then we go down to try to make the same changes to all of the other steps. And finally, what's interesting about it is that we managed, by making this change, we've managed to reduce the cost by about half. So we got it from about, so we basically got half of the numbers you see here at the top. But in terms of actual running time, these simple optimizations got us down from 12 minutes execution time for that query to 38 seconds. And that's enormous. That's exactly, like, if you think about it from an analyst point of view, or someone who has to run these queries and iterate on them and change them frequently and run them again and again and again and again, the 12 minutes can easily accumulate to days of running a query, going to grab coffee, coming back 12 minutes later, make a small change and run it again. It's just impossible and so backwards and not at all agile. And if we're able to optimize that, it's really not about, in my opinion, not about optimizing the performance of the database. It's about optimizing the quality and efficiency of the people who use the data and get them better results. So finally, it is interesting to note that there is no correlation between the improvement to the cost to the actual improvement in the runtime. The cost is just an indication of where the database thinks it's going to spend the most amount of time, but it doesn't necessarily tell us how much exact time is spent in every step. So in this example, you can see we've improved the cost by about 2 times, but improved the overall runtime by 18 times. So let's just try to think about how you automate all of it. And really, I will need to wrap up here very, very fast. But hopefully you will have the slides and you can hit me up afterwards with more questions. I'd be happy to elaborate if you're interested. So the way that we automate all of this into a continuous integration process is basically by a 2-step process. First, we have this analyze code. What it does is it reads the output of STL explain and STL scan periodically, like we run it again every couple of days. And we read all of the data and we generate an analysis table out of it. And the analysis table is a table that tells us basically it has the following columns. You can see it on the right. It has a role for each query, and within each query we have the time when it was executed. We have the table name, the column name. So if a query touches multiple tables and columns, it will have multiple entries or rows. And finally, it has 2 float numbers, which is the filter cost and the distribution cost. Filter cost is what I was saying in the beginning. We get it from STL explain. We look at how much time we've spent on it, and we basically multiply it by the inefficient time, like how much time, how much of that time is really spent unnecessarily because it's not sorted, because there's a big gap between the pre-filtered and post-filtered number of entries. So we come up with this coefficient, right? If you can think about it like this, for how much time this was spent on, or what was the cost of filtering that specific column on that specific query. And we do the same for distribution by looking at the joins. So we look at the joins, we look at the cost, and we come up with the same with a similar coefficient. And we just run this code over, like, periodically to generate this table. Then we have a different process that runs every couple of weeks. We call it rebuild. This process reads the explain analysis table and figures out, like, sorts it by the distribution cost and the filter cost to find, like I was saying, the one distribution key that will give us the best possible outcome. So the one that's most expensive, probably. Obviously, as a sum for all of the queries that we're actually running, right? Because I don't want to have a one-time query have too much of an impact on the final result. So we sum them all up, and we end up with the actual time. How much time did we spend joining that field, or how much time in the past month or weeks or couple of weeks, or how much time we spent filtering that specific column over the past month. And based on that, we can find the top ones where we spend the most amount of time doing joins and doing filters. And that really gives us the one distribution key per table. And then, as I was saying, we can really think about it. The output of this rebuild is basically picking for each table, after sorting and doing the sum, we pick the distribution key and sort keys that will give us the best possible results. We can pick multiple sort keys, so that's easier. Distribution keys is a bit more difficult because, you know, we can just pick one. So we might, if we pick one, we might hurt other queries that are maybe currently optimized. Once we have that output, we can obviously apply the changes and change the sort key. And finally, like, as I was saying, just something to think about. I think I don't have much time to elaborate on it, but applying the changes to the table is also kind of difficult. You can't just change sort key or distribution key because you must define it when you create the table. So really the way to do it is to modify, like create a new table, copy the data over, make sure that new copy commands or new inserts are coming into both tables, basically. And finally, I think the most critical part is making sure that we are not hurting performance. So the final step that we have in our CI cycle is to replay some of the queries and see that the results we are getting are on par or better, and if we didn't ended up ruining something that was working probably better before. And that's what we do. We obviously do that by, it helps us reason about how many times back we want to look at, or how we compute the coefficient to give different weights to different types of queries, stuff like that. But we basically optimize the script, we don't optimize the actual table. I think that's pretty much it. I'm sorry I had to really be fast. Usually I have more time. But I think the main takeaway here is not the specifics of how we're doing it, but really about how we think about data warehouse that, in my opinion, is not on par with how we think about any other technical development task. It's still really dated and manual and old, and I think we can really think about it differently by not thinking about what are the changes that I need to do, but what are the processes that will automate these changes. And and it applies to everything from, like I was saying, compression data types, stuff like that, to optimizations of queries, to maybe scaling, to monitoring, backup, anything you can think about. Pretty much it. We are in terms of the future. We are, at Panoply, we are building these kind of tools. This is what we're all about. So I think there's a lot of room for new frameworks and ideas and processes to be implemented, but and we're just starting to uncover what can be done to automate data management. But that's it, guys. I'm sorry for starting late, and I'm sorry for taking a couple of more extra minutes, but that's it. Let's see if we have any questions here. Yeah, hey.
Yeah, it looks like we do have a couple of questions that have come in. Roy, are you able to see the questions there in the questions panel?
Yeah, I think so. Let's see. Okay, there are a couple here. So yeah, I think we will send out the slides, Chris.
Yeah, we can definitely include a link to the slides in a follow-up email that we'll send out so that everybody has a chance to kind of go back through those at their own leisure.
Okay, perfect. So you guys can go over it, and if you have any questions or want to do a follow-up discussions, I'd be happy to brainstorm with you and maybe help you figure out what we're thinking of at Panoply. And we can think together of other things that can we can automate. So let's see. There was a question here about what are the monitoring tools that are in place for Redshift. I think there's a couple that AWS provides. I don't think it's enough, but it's definitely a good place to start. So Redshift has a bunch of monitoring tools, mostly focusing around the infrastructure. So you can see how much CPU is being used, how much disk is being used. You can see how much memory is being used. You can set thresholds on it, so you'll be notified if you have something that's running for too long or taking too much CPU. The tools that I think are missing and that we need to build ourselves are tools that are more around the data itself. Like I was saying, simple questions like, what are the top most used tables in my database, or how often they are queried, or if they're usually queried by like filtered by a certain key or a column, or if they're grouped, if they're joined, stuff like that. How many queries we have concurrently, or at any given time frame, stuff like that. I think helps us reason about how people are using the data. Unfortunately, I think that's kind of missing. Redshift does have a lot of great, I would call it like internal tables that you can query and get all of this data out of. So you can easily just run a SQL query that shows you, for example, the history of the queries being executed, or for each query, what exactly did it do? What exactly? How did it do the join? How did it do the scanning? Anything else, like what the users are doing? You can really deep dive into it, but it's not a monitoring tool, just raw data. So to turn it into a monitoring tool, you have to, and at least that's what we did. We just built these processes that collect all of this data and basically allows us to set thresholds on it and build charts out of it and get notified when something changes, like how people are querying the data. Unfortunately, that's pretty much you have to do it yourself. That's the case currently. Let's see. There's another question here. If most of my queries run fast enough using default this style and no sort key, will there likely be any big problems I might encounter if I add them later rather than prematurely? Right. So the question is really about, do we want to pre-optimize ahead of time when we really don't see an issue? or should we do it later? I think, to be honest, I think there's no need to pre-optimize. Like, I don't think you should, especially not manually. Like, I especially don't think you need to try to reason about. That's such a rabbit hole. Like, if you try to reason about what are the type of SQL queries that people are probably going to run in the next year, that's a question that you will make the wrong. You will have the wrong answers. You have no idea how the organization is going to change and what's going to be interesting tomorrow. So I think that we as technical people need to think about how do we build tools, how do we build processes that adapt and not, try to, it's kind of like waterfall versus agile, right? You don't want to build something that, you spend a lot of time to do research and figure out how it's going to be used, and then have something that's really rigid. You want to have something that you don't have to spend as much time in the beginning, but much more adaptable. Um, so I don't think you need to optimize prematurely. Um, but I do think that what you do need to do early on is make sure that you have the right tools to know when you start having performance problems. Because I think from our experience, most of the companies we work with, they don't usually know. They don't know that they have an analyst spending 2 minutes on a query that really should take 10 seconds. Because the analyst, he's running tens of queries or hundreds of queries a day. Um, he's sometimes not as tech savvy, just assumes that this is it and that's what he has to live with. And he wouldn't necessarily complain unless it becomes really unbearable. So I think we need to just have a way to know what people are experiencing. And that goes back to the previous question about monitoring. Like, I think, we want to be able to know the average query time, for example, or the median query time, maybe per user, and have a threshold on it, and be notified when someone is running a query that runs for 2 hours and he doesn't get a response, or even 2 minutes on average for a query that really should be 10 seconds. Um, so I think prematurely start with great monitoring and a system that will allow you to adapt. I would say that there's one kind of advantage to doing the premature optimization, which is, but it's really, I think, not really an issue. Um, that it's really difficult in Redshift to change sort keys and distribution keys. And you basically can't do it. You have to create a new table and copy all of the data over. So you might argue that if you do it ahead of time, when you create the table for the first time, you will save yourself the need to build a complicated process for being able to make this change and copying all of the data over. But I don't think that's the case. Like, I'm pretty sure that eventually, and probably like soon after you create the table, you will end up anyway with the need to make changes. So you will have to, in my opinion, you will have to pay the cost of building something like that anyways. So in that case, I don't see much value in premature optimization. And I think that's it.